So VG has joined again. I think there was some network issue or something. So VG, do you have any question? Do you have any doubts? If you can hear us. You can simply unmute and ask or write in the chat.
Actually, this 4 o'clock is a tiffin time, and I remember that this mass, and when I was at IIT Kanpur, that time this mass used to open at 4 o'clock, so all of us used to rush.
At 4 o'clock for the snacks or
Yeah, it's
yeah.
next, yes.
So actually, I wanted to. So since we are not having I mean many participants in the live sessions, what I wanted to do was to I mean put some examples together and just go through them and record it and put it on the NPTL. I mean, so this is what I as a TA I have to do. Uh,
Okay.
I find that this year, I mean, we are repeating the assignments from the last year. I asked Rajni ma'am. So then I'm not sure which type of problems I should uh, I mean I should solve here in the live session because I thought that I had this last year assignments from the NPTEL website, but they are again given this year, so I cannot solve them because then students will just look at the
Copy.
video and yeah and copy it. So uh, if any one of you can provide me with some some problems that I can work and solve them here live, that would be better, I think. Related to the lectures.
Maybe you can try solving them after the assignment submission date is over. Anyway, it will be useful for the exams.
Yeah, that can also be done. So like
That,
I solve 1 week later the
yeah, 1 week later, because already so many weeks have gone by, so
yeah,
you
yeah,
could
yeah.
now do for the previous weeks.
Yeah, that can also be done.
So, Rajni, what you can do for maybe 10-15 minutes, you can try to answer some of the questions that person has asked.
Yeah, that also you can do. Anyway, if he's not here, I'll record. I'm recording this
He's
session,
not around, Mohit. Okay.
so we can put it on the recording. We can put it on the channel on the website. So
Okay, I have mostly answered all his questions on the discussion forum, but I'll have to open. Let me look up for the problems. Just give me a minute.
you can, if you want, you can share your screen also.
So, Rohit, I will again learn from you that how to, because I have to give a presentation somewhere
Okay.
and using, so I will, first day I did it
Yeah,
with
yeah.
your help. So, I want to learn that again. So, what are the steps involved?
Okay, okay.
So, suppose I have made one file,
Mm-hmm.
PPT file.
Mm-hmm.
So, I have to open that on the desktop first.
Yeah, open that and then go to come here to the Google Meet
Hmm.
and then in the middle you have this present now button
Hmm.
in the middle center,
Hmm. There
and
is one upper arrow.
yeah, that one, present now.
So I have to click there.
Yeah, then when you click that, it will ask you three options. There is an entire screen option on the right.
Hmm.
You see it, entire screen. Choose what to share. There will be entire
Acha,
screen.
entire screen.
Yeah,
Okay.
then you select the entire, choose the entire screen,
Okay.
and there will be a small window open. Click
Ah,
on there, and then there will be a share option in the lower
share.
right part.
And then it will ask for that file.
Yeah, and no, then you simply go to your PPT where you have opened. It will show us.
Okay.
Whatever will be on your screen will be visible to everyone after
Okay.
you
Okay.
share your
Okay.
screen. So you don't have to do anything after this. If you want, you can try sharing here.
So I have to again open that, no?
Yeah, the PPT you can open, and then you can come back here and share.
So I have opened that on that one. Then
Yeah.
this entire selection, and then here, then share.
Yeah, now we can see your screen. So now you go to the your PowerPoint, it will be visible to us. Yeah, so it is
You can see,
yeah,
you can see that
yeah,
it's
and
changing.
yeah. It is changing, and
Oh,
you can go full screen if you want slides, so you can do. Yeah, now it is in full screen.
then I can come back by stop sharing.
Yeah, yeah. Now it will stop sharing.
Okay, okay. Now I think it's yes, done.
Okay, so I'll take up maybe some few questions from what was asked in discussion forum.
Hmm.
Uh, so since Ojas and Vici, they do not have any doubts as such. So one of the questions that is asked is that when should we use the uh, what is a thumb rule, or when does the relativistic mechanics apply? So here, since we are dealing with charge particles and their rest mass is very small, so as soon as the kinetic energies they become comparable to the rest mass, even before that, the relativistic mechanics apply. So the thumb rule is that you should use wherever possible. You should use. It is always safe to use the formula for relativistic mechanics because if I say 10, let's say 10 MeV, or let's say 100 MeV, 100 MeV electron is highly relativistic, so it's already become, the velocity has become close to the velocity of light. Whereas if you see 100 MeV proton, it's both Newtonian mechanics and this will give roughly similar results. This one slight variation will be there. Very slight variation will be there. So for accelerators, it is always better that you should use relativistic mechanics for any formula. I mean, for any problem, it will always give the that, because relativistic mechanics is always correct. It will always give the correct result. And whenever the energies are kinetic energy is comparable or slightly less also, then you can start with relativistic mechanics. So another question.
Now, Rajni, what is the, is there any harm if suppose we at very low energies also we use
uh,
relativistic mechanics? Okay, there will
no,
not be
no
any
harm at all. It is
continuation
okay.
voltage.
The answer will, yeah, the answer will be correct. I mean, it will give a correct answer. So at low energies, both Newtonian mechanics and relativistic mechanics converge.
So relativistic
So it is
mechanics
always,
because
that's
you
what I
don't
said.
change
It
the
is,
energy.
yes, so it is better for accelerator physics that you, because electrons become relativistic even at 1 MeV or so. So it is always better that you use relativistic formula only for accelerator physics. Okay, then somebody has asked, zero mode cannot be realized by applying voltage. So there is this electric field in every direction, and it cannot be applied. How this field is, such type of field is applied. So in pi mode, the drift tubes are alternately connected to the RF source. How do we get zero mode electric field same in every gap? So by using a Vidro type of linac, you cannot get the pi mode type of structure. Okay, so getting the pi mode type of structure, you have to go for electromagnetic waves. So Vidro, when he first made the linac, he connected the voltages directly to the drift tubes, and that is how he was able to get a pi mode structure. Now, if you want to get a zero mode structure, that means the field is there in every gap. In that case, what you have to do is you have to you have to use the high Q cavity, conducting cavity, put electromagnetic waves inside that. Standing waves are set up, and then use the, let's say, for example, you could use the TM010 mode, and in that you have Ez as a function of Z. If you see, it's constant. Then you put in the drift tubes there, and in at a particular instant of time, in every gap, you will get the fields in the same direction. So that is how you can get the zero mode structure in a linac. Okay, another doubt is why bunch size is kept small. Okay, so now even though we can use the entire positive cycle for acceleration, or at least the one-fourth of it, because if you use, you can use from your synchronous phase from minus pi by 2 to 0. 0 to pi by 2, you have the problem of phase stability, because you know that the early and late particles, they will start diverging about the synchronous particle. So you could use minus pi by 2 0, pi by 2 to 0, but you do not use, still you do not use the entire cycle, you use only a small portion of it, because if you use minus pi by 2 to 0, then some particles will have maximum energy gain and some will have zero energy gain. And there will be a huge, and other particles will have intermediate energy gain. So there will be a huge spread in the energy of the bunch. So by definition of beam, the spread in energy of the particles should be very small, typically of the order of 1% or so. So if you use the entire bunch, then, I mean, if you use the entire one-fourth cycle, then the spread in energy will be very small. So that is why bunch size is kept small, such that only small variation in the field is seen by the bunch. Okay. CW and high duty cycle are possible at high gradient. So if you go, the biggest advantage of superconducting accelerators is their efficiency is very good. So let's say you're putting some power into the accelerator. So out of that power, large portion of that power in a normal conducting accelerator will be dissipated in the walls of the cavity. So I've given examples of the LiPA RFQ and design values of LiPA RFQ in detail. So we see just about 20 to 30% of the RF power goes to the beam, remaining 70-80% gets dissipated in the wall. So now in hello, okay, I think I lost connection.
Yeah, we lost you a little bit in the last sentence. Can you repeat it again?
Okay. So yeah, I'll repeat. In a normal conducting accelerator, if you are operating CW and you try to increase the accelerating field or the accelerating gradient, it's known as the accelerating gradient. If you try to increase that, then the power dissipation will increase even more. So cooling that is a big issue. So as I gave numbers for the LEPA RFQ, we about 400 kilowatts of power is dissipated in 4-meter long structure. So this is a huge amount of power, and it has to be removed by cooling. Otherwise, the dimensions of the structure will change and frequency will change. And if the frequency changes, whatever RF power you are feeding into the accelerator will get reflected back. So power will not go into the accelerator. So cooling is very important. So the normal conducting accelerators are limited by how much heat you can remove. So even if you can, let's say, go to a higher accelerating gradient, but you are not able to remove that heat and the dimensions will change, then you cannot go to high accelerating gradient. For CW operation, because CW operation, the dissipated power is very high. So if you have seen, I've shown in a table in the lectures that so we only power will go to the beam. So the power dissipation is very small. So you can afford to go to high accelerating gradients. And you can operate CW because even whether it's CW or pulse, the power dissipation is very small. So you can operate CW and you can operate at high accelerating gradients. In case any of the students have any, I mean, whatever I'm speaking, if you have any doubts, you can ask. Okay. So that is why CW and high duty cycle you can accelerate in superconducting accelerators with high accelerating gradient. Okay, a similar question already answered. Okay, what is the difference between a resonator and a cavity? So basically, resonator and cavity are same, but if you see in literature, generally for TEM modes, cavities that are in the TEM modes like half wave resonator, single spoke resonator, quarter wave resonator, the term resonator is used. And for TM or TE class, normally cavities is used. So they are same. Actually, resonator and cavity means the same.
Ojas has asked something in the
The
chat.
yeah, the temperature of just let me see. The temperature of heat dissipation will be how much? Why? Which coolant is used? Generally, water at low temperatures, maybe 16 to 20 degree is used. So we do not let the so temperature has to be maintained. The temperature of the cavity has to be maintained at room temperature, normal temperature. So it depends on the power dissipated. Like I said, 400 kilowatts without cooling, the temperature may go to some 70, 80, 60, 70, 80 degrees. So generally water is used. So and water at 16 degrees centigrade or 20 degrees centigrade is used, and to cool down. So it should be at the operating temperature, the normal room temperature, because any heating will.
Rajni, you may like
Yes.
to add that it is not the normal water; it is a low conductivity water.
Yeah, it is low conductivity water because these are all conducting materials, and I mean currents are involved flowing on the surface of the cavity. So that is why you have to have low conductivity water, and it is to be at low temperature of the order of 16 to 20 degrees, and uh, normal to bring the cavity back to normal temperature. Is that okay? The other questions are quite trivial actually. Okay, I think that's all. Unless something very, if somebody wants to ask something. So, do you have any more doubts, Ojas and Vichi?
Yeah, maybe students can later ask in the discussion forum also, following questions if they
Yeah,
have.
yeah. You can go and see the discussion forum also. If you have any doubts, you can always
Yeah,
post
yeah,
there. So, I usually post in a couple of days, and then we can take it up if anybody has doubt. We can take it up in the discussion forum also.
yeah.
I mean, in the this live session also.
Okay, I think. Oh, there is one question.
What is the range of energy? Neutron collider at CERN, there the maximum energy is of the order of 7 TeV. So, range of energy means its maximum energy, I can tell you, is 7 TeV. So, it's a synchrotron.
So, so the
So,
center
you'll
of
learn
mass
about the
energy is,
synchrotron
I
in
think,
future lectures.
it is 14 TeV, the center of mass energy for proton-proton collision.
Yeah, collision. Yeah, when they collide 7 TeV beam onto 7 TeV. So, when they collide, it is 14. Okay, just has left.
He is joined again. I think he is having some trouble in network.
7 TeV. Yeah. Okay, so 7 TeV beams colliding, 7 TeV beam colliding with a 7 TeV beam at CERN.
And for heavy ions, we have 2.5 TeV beams. So this time we have increased that. This time we have gone to 2.58, 2.518, 2.68, sorry, 2.68 TeV beams for heavy ion, for lead pollution.
Okay.
So we are going to have a heavy iron run starting from next month at highest energy.
Okay. Yes.
Rohit, that energy for heavy ion must be per nucleon, isn't it?
Yeah, that is per nucleon. So
So
yeah, the
total energy will be pretty high.
yeah, it is pretty high. If you for the whole nucleus, it is much higher. It is so the center of mass energy is 5.36 TeV per nucleon. So yeah.
And for heavy ion, what is the mass? Which
Uh,
ion?
oh, it is lead ion.
Lead ion. So the energy will be hundreds of TeV.
Yeah, yeah, yeah. So, so the mass is around. So there are around 240,
208.
200.
208, yes.
Yeah, 200 neutrons and protons. So it's pretty high.
So then it will be competing with the FAIR project in Germany.
Yeah, but I think FAIR project is a different kind of. It is a target and fixed target experiment, right?
Yeah, fixed target experiments. Yes. So center mass energy there is less.
Yeah. They want to study this cold baryonic matter at FAIR. So, like the condition inside a neutron star, I mean, compressed, compressing the nucleus so that they can get a condition like quark gluon plasma applying by pressure. Whereas in our experiment, we produce quark gluon plasma by increasing the temperature, not the pressure. So it is a so
So
that's the
one
difference.
Suryan has to be sent there also.
Oh, yeah.
Basically, it is fusion reaction then.
Hmm. Yeah. Okay, so Ankita has joined. So, Ankita, do you have any questions from the lectures or any general doubts from the course? You can ask.
Sir, good evening, sir.
Yeah.
Sir, I have a query about the exam.
Oh,
I just want to know that exam is subjective or objective.
so exams will be the same like assignments, right? Multiple choice questions will be there.
No, it will be all objective type. For each question, there will be four options and you have to choose one.
Okay, sir. Thank you, sir.
You don't have to write any details. You have to just tick mark.
Okay, sir.
Okay, so anyone else has any questions? Ojas, VG. Think if not,
No,
maybe. Yeah, hi, VG. You want to ask something? Okay, so if there are no more questions, maybe we can close today's session. Uh, and yeah, Rajini ma'am suggested, I will what I will do from next time, maybe I'll prepare some examples from previous weeks. So for example, in the next week, I'll have the examples from this week's assignment, and I'll try to solve them. So that I can do. And yeah, but first we can maybe clear the doubts of the students. If there are no, if there will be few students again, then I will take over and I will go on with the examples.
Next week, I understand that third module will start, isn't it?
One more question is there, perhaps in chat
Oh
box.
yeah. Ojas has asked one question.
Which type of accelerator is used for fast breeder reactor? Okay, do you mean an accelerator driven system or so reactors are actually independent of accelerators except when you have an accelerator driven system. So are you talking about an accelerator driven system? Okay. So in an accelerator driven system, you have a linear accelerator, 1 GeV energy, and 1 GeV energy and some tens of milliampere current. Okay. So typically maybe 10 milliampere or so of current is required for accelerator driven system. So if you see, you have higher energy accelerators already existing in the world. For example, I mean, there are even higher energy, like 7 TeV LHC at CERN is at higher energy. But if you see, there is no accelerator at present for ADS. So this is because there are several requirements from the accelerator for ADS, which are like non-conventional. So one is that it has to be, it should give a CW beam. So I have explained the difference between CW and pulsed in my lecture on superconducting cavity is there. So CW means power dissipation is huge. So you need to go to superconducting in cavities right from the beginning. So one is it should be CW. The other is such an accelerator should be very reliable. Reliability is a big issue. Most accelerators, they are designed just for doing some experiment maybe, or some application for some application which does not require it to run for long periods of time at a time, for very long periods. Okay, just maybe for a couple of days, or maybe at the most for a week or something, some experiment is going on, some application is going on. But ADS, since it will be used for power production, so there the reliability issue is very high. So it needs to run 24 cross 7 for months at a time. So most accelerators now, if you see, they are not, they do not have the reliability of this standard. So ADS accelerator has to be designed with very high reliability also. So that means, each and proper arrangement has to be made. Like if some component fails, what will you do? So what is done is that, let's say one cavity fails, and so you don't want to shut down the whole accelerator at once. What do? You adjust the fields in the neighboring cavities, and then you keep it running, you get the same similar energy. So all that analysis has to be done. So this is not being done for other type of accelerators which are running today. So for ADS, you need a linear accelerator, because a linear accelerator will give you CW, and you need high current of the order of 10 milliampere. So that is why you have to go for LINAC, and it should be highly reliable. So I hope it answers your question.
Maybe you can also add that for fast breeder reactor based systems, you don't really need accelerators. See, this same job can be done independently while fast breeder reactors.
Yeah,
In
yeah.
fact,
I think he meant accelerator.
there is
Yes,
always a fight between fast breeder people and the ADS people.
yes, yes. So I think he meant actually accelerator driven system as he's
ADS, he
clarified
meant
earlier.
ADS. So that,
Yes.
but that in ADS, the reactor is not fast breeder. ADS reactor is not fast breeder reactor.
Yes. Okay.
And also, I think the benefit of waste will also be there in ADS. Long-lived waste will be lesser.
Yeah, exactly.
There actually waste is also used as fuel in ADS. That is the advantage, one of the big advantage.
Yes,
Yes. It is also transmuted.
Because there is a big spectrum of neutrons. So cross sections are pretty high at different energies, where
yes,
this
yes,
waste also is consumed.
yes, yes. And the factor of
Basically,
K, that is again
actually,
advantage.
that is the advantage in fast breeder reactors because
Yes,
some nuclei which require fast spectrum, that is already there. While in this ADS system also it is there, but you slow it down by some means, and then you use it. Because in ADS, since the neutrons are produced by spallation neutron source, so a spectrum is there up to very high energies, which may not be very useful, and that you slightly slow it down, but not to that thermal energy or something like that, which is normally used in the conventional reactors. But fast breeder reactor, it is already there. Fast spectrum is already there to that reasonable energy. So both can be used independently for using the clearing the waste, converting the waste into the fuel and generating energy.
So yeah, I think this answers Ujja's questions.
Rajni is okay, no?
Yes, sir.
Because this fast breeder reactor, people say we don't need accelerators.
Yeah,
And
yes, sir.
of course, the accelerator based, that means ADS is more efficient as compared to fast breeder reactor from the safety point of view.
that is the thing. K can be less than one.
K is normally much less than 1.
One, yes.
But then if K becomes too less, then your current requirement goes up.
Up to point 9, 8 and 9, 9 like that.
Yeah, 9.8 now people are designing for 9.8. Earlier, for example, Carlo Riviere designed for 0.95, and all the demo ADS were designed for zero point 0.9, but they were only demo systems. Practical things, Carlo Rubia designed for 0.95. But now people are saying that we can take care of safety part with 0.98 also. In fact, some people are saying 0.99 also. That is too much. Actually, that risk is involved in that. Okay, Rajni?
Yes, sir.
Amlendo, I saw a report recently which he considers this 0.99 also. What,
Yes, sir.
what
I also see somewhere in that 0.98 and 99 to reduce the requirement of beam power from the accelerator.
the 0.98 has become standard now, but
No, yes,
people
yes.
have started talking about 0.99 also,
So,
which is
yes.
very unsafe. Other
Yes,
people are
yes.
not agree with that. Yes.
Okay, so do we have any more question, Ojas or Viji or Ankita?
No, sir.
Okay,
No, sir.
okay. What about Ojas? Do you want to ask anything else? Okay. Uh, so it's 1 hour already, so maybe we can close today's session and see you all next week.
Thank you.
Thank you, sir. Thank you all.
Okay. Thank you and bye.
Thank you.
Okay, thank you everyone. Bye.
Thank you, ma'am. Bye.
Thank you, sir.